Welcome to our video on time series analysis. We'll start by understanding what time series data is MATE. It's data collected sequentially over time. In agriculture, this is crucial for predicting crop yields, understanding market trends, and much more. However, analyzing such data presents unique challenges like autocorrelation, seasonality, and non-stationarity, which we'll explore in this module. Let's dive into the Gauss-Markov theorem, a cornerstone of regression analysis. It states that under certain assumptions, the ordinary least squares estimator is the best linear unbiased estimator. However, time series data often violates one key assumption: independence of errors due to serial correlation. This means past values can predict future values. We detect this using the Durbin-Watson statistic and autocorrelation function plot. How do we tackle serial correlation? We can use differencing, transforming variables, or adding lagged variables into our model. This is particularly vital in agricultural data to correct for seasonal and cyclical trends, like adjusting crop price data for seasonal variations. Depending on your application, you may want to smooth how prices vary in the short term, or you may want to smooth longer trends like the normal variation in commodity prices throughout the production year. Moving averages help us smooth data and identify trends. It's calculated by averaging a number of points around each data point. For example, in agriculture, we might use a moving average to smooth out rainfall data, helping us understand underlying trends. When we use OLS in time series models, we must consider trend component seasonality and error components. The estimation process follows typical regression analysis, but interpretation requires a focus on how these time-based components affect our agricultural variables. Panel data is a more complex form of time series data, involving measurements over time across different entities like various farms or regions. It's powerful in agriculture for analyzing wide-spanning data while controlling for variables that are constant over time but vary across entities. Let's apply what we've learned using corn prices as an example. We'll use a moving average to smooth out seasonal effects. We will dedicate a separate video for the OS estimation. This helps us analyze trends in seasonality in corn prices, offering valuable insights for decision-making in agriculture. First, we generate some fake weekly corn price data. We calculate a 3-week moving average by taking the average of the first 3 weeks, then move forward a week, and so on. Note that we lose 2 observations with these differences. We see that loss of 2 observations, but also see how the moving average smooths out the change in price. You might cover what to do with this information in an agricultural prices class.